Hello, welcome everyone to today's Colchin seminar. It's my real pleasure to introduce David Meretzky from the Los Andes, sorry, and he'll speak about D-torsors in differential Galois theory.
Okay, thank you so much, and thank you guys for the invitation. It's really nice to be back here and speaking. Um, okay, so so this is kind of a report on joint work with Omar Leon Sanchez at the University of Manchester. And so I'll start by talking about some characterizations of both Gal or usual ordinary Galois extensions and differential Galois extensions. Um, and so this is okay. So yeah, okay, click. Okay, in the usual. So okay, so in for usual Galois theory, we have the following characterization or slash definition. So a Galois extension could either be thought of as a normal separable finite extension or as the splitting field of a separable polynomial. Um, and so the first class of differential field extensions admitting a good Galois theory is the Picard-Vessio extensions. And so to give a kind of anachronistic definition, one could define a Picard-Vessio extension as a strongly normal extension, which I'll say what that is later, with such that the constant field of the upper part of the extension is the same as the constant field of the lower part of the extension, and such that the Galois group is linear. Okay, and then this is equivalent to the usual definition of a Picard-Vessio extension being a no new constant extension generated by a fundamental system of solutions to a homogeneous LODE. Um, but this kind of left side characterization more abstractly of Picard-Vessio extensions is anachronistic as a definition. Kolchin came up with the definition of strongly normal extensions and then had to figure out which class of extensions these correspond to. So he defined, on this left-hand side, this condition of strong normality together with no new constants. This gives a class of extensions which admit a good Galois theory, and then it takes some work to figure out uh, that these are exactly the ones generated by solution to a logarithmic differential equation on a torsor for an algebraic group over the constants. And so the characterization of PV extensions inside of strongly normal extensions. So uh, from the first slide, the second definition of the first slide is closer to Kummer's theorem characterizing Kummer extensions. So um, so let K have enough roots of unity and also actually let P be relatively prime to the characteristic of K, but I just didn't want to type that. Then L over K is Galois and cyclic of prime order if and only if L over K is generated by a solution to a polynomial equation of a certain form. So this kind of echoes this definition of Picard-Vestio extension, where you have, you ask that it be strongly normal, but you also ask that the Galois group have a certain shape, and then you know that um, you get a more specific class of equations than just among the equations giving rise to all the strongly normal extensions. Okay, and then yeah, and so this is so Kummer's theorem is sort of closer to this definition slash characterization of Picard-Vessio extensions. And then Kummer's theorem, we'll just note, is an early instance of Galois cohomological methods. And likewise, to characterize the strongly normal extensions, this is where Kolchin, Lang, Kovacic, and I guess sort of implicitly Bialy-Nicky, Birula, and others are starting to initiate Galois cohomological methods into differential algebra. And so Kolchin and Cassidy defined differential algebraic groups and differential algebraic torsors. And Kolchin and Kovacic defined after several iterations of redefinition of this cohomology set for a differential algebraic group G over K, they define this cohomology set to be the K isomorphism classes of differential algebraic torsors for G. Okay, so and defined over K. Um, okay, and Kolchin proves this theorem in his second book, uh, which says which we refer to as Kolchin's cohomology theorem. It says that for an algebraic group for G, an algebraic group over a differential field, then the differential Galois cohomology set, so K isomorphism classes of differential algebraic torsors for G, is in bijection with algebraic torsors over K for G. And so as a consequence, if K is algebraically closed, or for example, if G is GLN, in either case, the algebraic cohomology here is going to be trivial, and so the differential cohomology is also trivial. And then these two facts give kind of well, they kind of okay, so if K is algebraically closed, then we get a stronger description of the strongly normal extensions. Before we were saying that they were exactly the no new constants differential extensions generated by a solution to a log differential equation on a torsor for an algebraic group. But if K is algebraically closed, then actually what we end up getting is that it's generated by a solution to a logarithmic differential equation on the algebraic group itself, which will on the Galois group itself. Now, in the PV case, the Galois group which we assume to be linear, uh, will always sit inside of GLN, and so one can always find a solution. One can always find a logarithmic differential equation on GLN, giving rise to that Picard-Vestio extension. So there's no, so here the assumption is that the field is algebraically closed, and here the assumption is that the Galois group is linear. Okay, so just to kind of to state first loosely our result, the point of the project that we were trying to do is to generalize to the generalized parametrized multiple derivation setting Kolchin's characterization of strongly normal extensions. And we also generalize Kolchin's cohomology result and give a cohomological condition for when the equation can be found on the Galois group as opposed to on a torsor. So when can the extension be generated by an equation on the Galois group as opposed to on a torsor? So the remainder of the talk is going to be a brief description of the D varieties formalism in the single derivation setting. And then I'll give a sketch of this kind of style of result in the single derivation setting. And then really there should be this is not what 3 is. So actually 3 should be then I'll state what our then I'll kind of describe the parameterized setting, and I'll state our results, and maybe I'll give a kind of sketch of the proof of kind of the parameterized version of Kolchin's cohomology result. But actually I'll give kind of a sketch of the proof that doesn't appear in the paper. So maybe okay. So maybe I'll give kind of a different sketch of the result, or maybe just I hesitate to even call it a sketch. Maybe it's just even maybe it's even just some intuition for why it should be true. And then lastly, I'll talk about some examples, both extant and missing from the literature. Okay, so uh, D varieties. Okay, so let K be a differential field and let U be a big, like a universal domain, like a big differential field, which is, I guess you model theoretically, we would say it's saturated. Okay, and so we'll work inside of this. But actually one could work inside of the differential closure. Okay, so let let V be an affine irreducible algebraic variety defined over K, and let's let F1 through Fm be generators of the ideal of V. Uh, okay, so then we define this tau of V to be um, something like the tangent bundle, but accounting for the fact that V is defined over a differential field, K delta. Okay, and so you should just think of, X. So tau of V is pairs where the first coordinate is coming from V and the second coordinate is a vector. So we're just thinking of this basically as like a twisted form of the tangent bundle. And we note that the derivation on 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 U, so on this big differential field, gives a map, gives a section of the projection map down. Okay, so it gives a section, so it gives a map from V to tau of V by sending a point X in V to X and then the derivation applied to the coordinates. Okay, and this is a differential algebraic section. This is not an algebraic section um, of the twisted tangent bundle. But it's a fact that the algebraic sections correspond exactly to extensions of the derivation of delta on K to the coordinate ring, K of V. And a D variety is a pair consisting of an algebraic variety, or we'll say irreducible over K, together with a section of this tangent bundle, equivalently an extension of the derivation to the coordinate ring. And a D group is where we assume the underlying variety to be a group and T to be a homomorphic section. So in this case, the twisted, if G is a group, then tau of G will also carry a group structure. And so we ask that the section be a homomorphic section, be a homomorphism as well as a section. And then a D-torsor is going to be a pair consisting of D variety and a D group together with a D action, um, which I'll describe briefly. So it's an action of the group on the variety. Okay, so if we have two D varieties, VS and WT, then and we have a K morphism phi from V to W, then this then this induces a map of these twisted tangent bundles. So this is like the derivative of a K morphism being a map between the tangent bundles. Okay, so we get this tau of V, which we think of as the derivative of phi, tau of phi, yeah, which we think of as the derivative of phi. And if tau of phi satisfies that if we start at V and we go upstairs to tau of V, and then we go over via tau of phi, it should be the same as first doing phi and then going upstairs via t. So if this diagram commutes, then phi is, and this should be the same phi, not var phi, then this is called a dimorphism. And so there's just a notion of a D action of a D group on a D variety. Okay, last set of important definitions with respect to D varieties is if we have a D variety, Vs, we define the sharp points to be the set of elements in V such that, well, we have two sections. We have the differential algebraic section coming from the derivation, and we also have the algebraic section, uh, which is coming from the definition of the D variety. So we just ask for the places uh, where the algebraic section and the differential algebraic section agree. And so this is okay. So for example, I'll call S sub zero the trivial section. So it's going to send every point of V to just uh, uh, the zero vector sitting over that point X. Okay, and so when we look at the sharp points, it's saying exactly, well, where are the places where when we apply uh, when we apply the derivative, when we apply the derivation, we get zero. And so this is exactly asking for the constant points of whatever differential field we're looking over. Okay, so usually people just conflate the notation and they'll write this S sub sigma as just I mean S sub delta is just delta, and they'll write S sub zero as I don't know what, just zero maybe. Um, or maybe they'll write it as S sub zero. But just to keep things a little bit because at some point we'll try to do actually a little computation uh and so it's convenient, or it's sort of it's slightly less confused to not confuse the notation here and the notation here and the notation here and the notation here. Okay, so that's the reason for a little bit of non-standard notation. Okay, so facts about D varieties. So let X be a finite dimensional in any sense, irreducible differential algebraic variety over K. Then there's a D variety, okay, such that X is differentially birationally equivalent over K with the sharp points of this D variety. Okay, so we have a differential algebraic variety, and we can find an algebraic variety together with a section S, such that the sharp points of this D variety give us more or less X again. And so this actually sets up an equivalence of categories between the finite dimensional differential algebraic varieties over K and the category of D varieties over K. And moreover, it extends to torsors. So let QH be a finite dimensional differential algebraic torsor over K. So this is a torsor cut out by, differential polynomials over K. Then there's a D-torsor. So there's an algebraic group G together with a section and an algebraic variety together with a section such that Q can kind of be realized as VS and G and H can be realized as GT. So to sketch this kind of okay, so when I say the theorem, what I mean is the left to right direction of Colchin's characterization of strongly normal extensions. So we're proving that if L is strongly normal and has no new constants, then it's generated by a solution to a logarithmic equation on a D-torsor. And so what we'll show is that it's generated by the solution to a sharp equation on a D-torsor. And moreover, we'll find coming out of the proof, okay, well, yeah, so really the content is to find a cohomological condition for when the equation actually is on the group itself. Okay, so all right, so we're starting with L over K being strongly normal and CL with no new constants. Okay, so that often that's part of the definition of strongly normal, but I'm just separating it and I'm thinking of strongly normal as being this automorphism condition, which I'll state more clearly in a slide or two. Okay, but okay, so the first thing is to apply the torsor theorem. And here I'm kind of thinking of a model theoretic version of the torsor theorem. Okay, so parts one and two of this sketch together will really be the kind of the torsor theorem as you would find it in van der Singer. Okay, but so first, okay, from this definition of strong normality, one can cook up two things. One can cook up a differential algebraic variety Q and H, a an algebraic group living in the constants, okay, with H acting on G, and such that Q is really the set of fundamental systems which all satisfy the same type over K. Or another way of saying this is which all satisfy the same, they all have the same, these are the fundamental systems of solutions which satisfy the same differential ideal. Okay. And then okay, so the first step is to apply the torsor theorem and okay. So the second step is more or less by the equivalence of categories. We know that Q sits inside some Z, some algebraic variety Z, and there's a certain section S such that Q is actually the sharp points of ZS. And secondly, H can be realized as the sharp points of a differential algebra sorry, of a D group with trivial section. Okay, so H is really the constant points of G. Okay, and I guess we're working over K. So L is J, so actually so one and two just directly give us that L is generated by a solution to a logarithmic equation or a sharp equation on an algebraic torsor for an algebraic group. Okay. Now, okay, so now look at this algebraic group. So H, this is really H. So this algebraic group and the constant points sit inside of all of the differential field points. And this is just a set of I'm thinking of this as a set of cosets. So I'm not thinking of this as having this quotient as necessarily having a group structure. So this is a short exact sequence of pointed sets. And this induces an exact sequence in Galois cohomology. Okay, so okay, so and here we're taking this Galois cohomology of Colchin. We're not taking the usual algebraic Galois cohomology because this is a differential algebraic group. This is just the group in the constants. This is the usual group in the constants. This is maybe all of its differential field points. Okay, so this is the set of cosets of the group in the constants inside of all of the field points. Okay, this is the set of torsors for the Galois group. So in particular, Q, which is the sharp points of which is the sharp points of this algebraic torsor is a class inside of here. Okay, so attached to the strongly normal extension that we started with, we get a torsor which shows up exactly as a class in this H1. Okay, and it goes into H1 of the full group G, which is again an algebraic group where we're looking at its differential field points. And so by Colchin's cohomology theorem, this because G is an algebraic group, the differential Galois cohomology is exactly the same as the algebraic Galois cohomology. Okay, so we're looking at Q. The class of Q lives in this first H1 term. So if the image of this class in H1KG is 1 for some reason, so for example, maybe K is algebraically closed, and so then the usual H1 is trivial, or maybe G is GLN, in which case this is also trivial, then that means exactly that this Z, this torsor is in the image of the map from the set of K defined. So really what this is K definable left cosets. Okay. So so without this K here, this is just the set of cosets of the group in the constants inside of all of its field points. And so what this is saying is, so if the image is 1 for any reason, okay, maybe this is trivial, or maybe the class just happens to land at 1. Then because the sequence is exact, right? It tells us that actually the torsor we were looking at is a coset, is just simply a coset uh of the constant points. Okay, inside of the group G. Okay. Now now the sharp equation, the sharp points are the kernel of the solutions to the sharp equation. So they're the kernel of this map, which is the difference of the two sections. So because this is a coset, this map is single valued on this coset. Okay. And because we assume, this is kind of coming from the definition of the long exact sequence in cohomology, that it's a K definable, it's a K definable coset. So take those two things taken together show you that the image has to be a K point alpha in the in the twisted tangent bundle for G, but sitting above the identity. Okay. And so and this coset is the set of solutions to uh to this equation. And so one can define a new section to be alpha plus the zero section. So this is taking place with the group operation upstairs in the twisted tangent bundle. And so what this is saying is that, okay, under this cohomological condition, so if the image of this map, if the image of this class under this map happens to be 1 for any reason, then there's a new D variety structure that we can put on G such that the torsor, okay, which a priori or initially was non-trivial, uh is actually uh the same as the sharp points of G together with this new D variety structure. Okay, so I'll make a comment, which is that G with this new D variety structure is not a D group. It is a D. Okay, so G with the trivial section is a D group, but this thing is not a D group. It's a D variety. But namely the section is not necessarily homomorphic. Okay. All right. Yeah. Okay, this is just a summary of what I just said. Okay. So, okay, so right. So, So this is the original theorem of Kolchin and Kovacic, really. Okay, so but stated in the language of D-torsors. So L over K is strongly normal, meaning for any sigma in the automorphism group of U over K, when we apply sigma to L is contained not in L again, but in L together with the constants of U. And also we have to assume that it's a no new constants extension. So I'm just writing out the definition of strong normality here. And over here we have over here we have that L over K is generated by a sharp equation on a D-torsor for a trivial D group, namely G. I'm saying the D group is G together with the zero section. So it's a D. So the group is a group in the constants. Okay. So 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 Anand Pillay generalized this right-hand picture uh and he said, okay, what if we drop the condition basically that the section on the group G has to be trivial? What if we allow other kinds of sharp points besides just constant points? And so then you get the jet. So let X be a finite dimensional differential algebraic variety over K. Then we say that L over K is generalized strongly normal if for any automorphism, the image of L is now contained in L, but also the field generated by the points of the set X. So we're replacing the constants with a different finite dimensional differential algebraic variety. And we ask that basically there's no new X points. And then, so the statement that this is equivalent to asking that L over K have no new X points and be generated by a sharp equation for a D torsor for a D group. Okay, that's exactly what I'm claiming. Like that's exactly what I'm claiming. So what do I mean by this? So this statement sort of is well known due to Anand, but Anand's theorem is under the condition that the field of constant that K is algebraically closed. In which case, the right-hand side says generated by a sharp equation on a D group. So if you look in the paper, if you look in his paper Differential Galois Theory 1 or his Pacific Journal paper where he kind of reproves some of this reproves this using the D varieties formalism. That's called it has a name that's very similar to the name of our paper, right? Okay. Anyway, that paper's from about 2000 from 2000 no from about 1997. Okay. The point is that the way that this appears in the literature is that it's under the condition that K is algebraically closed, and the consequence is here that it's a sharp equation for a D group. And in the introduction to the paper, Anand says it would be good to do this theorem in this form, but we leave that to other to another for another day, basically. Um, so, okay, so Omar Leon Sanchez read that part of the thesis where I sort of wrote about this stuff and said, let's do this for the parametrized category. So that was kind of the birth of this project. Okay, so let me say some things about the parametrized category. Okay, so we're working in a differential field together with n commuting derivations, and we're going to partition them into a set D and a set delta. Now, working with differential polynomials, one has a notion of delta algebraic groups and delta varieties and delta torsors, G. And there's a notion of a relative tangent bundle in this setting, and such that when you apply this new set of derivations D, this gives exactly a section of this relative tangent bundle. Also, one can consider cohomology with respect to, measuring pi algebraic torsors or measuring delta algebraic torsors. And so a theorem of Omar from his thesis, I believe, sets up the same equivalence of categories that we saw earlier for D variety. So for X, a K irreducible pi variety or group or torsor, with a condition playing the role of asking that X be finite dimensional, namely it's a technical condition that delta bounds the pi type of X. Okay, but in your head, you could have this as being more or less kind of finite dimensionality uh, of X. Then there exists a then there exists a relative D variety, parameterized D variety, such that the underlying variety here, W, will now be a delta variety, a delta algebraic variety, and such that uh, X is pi rationally isomorphic to the sharp points of WT. And this gives the required equivalence of categories. Okay, so Omar and I basically more or less as a consequence of this equivalence of categories, give uh give a parametrized version of let me just check if is Omar in the audience at this point.
Yeah, I am. I am.
Hi, hi. Okay, so I just want to apologize, Omar, because this is not the proof that we give in the paper, and I'm not and I yeah, and I shouldn't even really call it a proof. I should call it kind of an idea for why this is true. But in fact, if you see something really really wrong with what I'm saying, maybe we can talk about it after. Uh, okay,
Okay, that's okay.
okay. But okay, so let G be a delta group. Okay, then the set of isomorphism classes of pi varieties of G is isomorphic to the set of delta isomorphism classes. Sorry, I'm sorry. What am I saying? Yeah. Yeah. Pi isomorphism classes of torsors for G, of pi torsors for G is the same as delta isomorphism classes of delta torsors for G. Okay. So let X be a pi torsor for G. Then X must have pi type bounded by delta. Okay, this is a result from Omar's thesis. Because G will have because this will be the case for G, I believe. Okay, and then by the equivalence of and then one just simply applies the equivalence of categories. So X then has to be of the form delta of T. And I think this is why we didn't, I think this is, if I recall correctly, maybe we talked about this, and this is why we didn't use this proof. But the idea is that G should have some relative D variety structure such that this is a D torsor, and then this is the relevant, and then WG is the relevant delta torsor. But maybe we didn't do this. Maybe we didn't do this in the paper because it requires us to find a D group structure on G, which maybe it wasn't so clear how to actually do that. So
I
we
mean,
give
maybe
it.
I can ask you at the end, but the thing in here is that G does not necessarily have pi type bounded by delta, right? The G itself does not
Ah,
necessarily have pi type bounded by delta, right? But I can ask you after the talk. Please
okay.
keep going, keep
Okay.
going.
Okay. Okay. Yeah. I really think there's something wrong with what I wrote here. So, and it's not what we wrote. That's not how we did it in the paper, but somehow somehow the intuition that I had in my head. So maybe this should just say something like more like intuition rather than proof. Okay. So and then this is the statement of the theorem. Okay. Uh okay. So let X be a K irreducible pi variety with delta bounding the pi type of X. Then L over K is parametrized, generalized strongly normal. So it's the same strong normality condition that appears in the generalized strongly normal setting, but we're working with pi many derivations. And then and then we showed that this is the same as L over K being generated by a sharp equation for a parameterized D torsor for a parameter for a parameterized D group. Okay, so I just didn't write for a parameterized D group, but it's a parameterized D torsor. Okay, sharp equation for okay. And then moreover, if the image of this class is one under the relevant map in cohomology, then L over K is generated by actually a solution on the is generated by a sharp equation for a D variety structure on the Galois group. Okay. Now let me just say that in Omar's thesis, he proves this theorem, but again under the hypothesis that the base differential field K is delta differentially closed, in which case the right-hand side says it's generated by a sharp equation on directly on this D group. Okay. So so okay. So part of the work was or the so the content the real content of the theorem is to drop any condition on K and then instead we get that we get the resulting that the extension is generated by a sharp equation on a D torsor. Okay, so then so we were trying to find examples, even in the strongly normal case, even in the usual strongly normal case, or even in the Picard-Vessio case, well, it wasn't clear initially that one could find an example in the linear case because, I mean, to me, I found this very confusing because if you're working in the context of if you're working in the linear case, one can always find an equation on GLN. Now, you might not always be able to find an equation on the Galois group, which is a linear group, but you can always find an equation on GLN. So for a long time, Omar and I were trying to look outside of the linear case in the strongly normal case, and we couldn't find an example, and we were having trouble building an example of where L over K is generated by a sharp equation on a torsor, not on yeah, really on a non-trivial torsor, not on the group itself, not for some D variety structure on the group itself. And
Can I add, David,
and
that the point is to find it such that this map is not to one. It's not something that doesn't map to one. Basically, it's equivalent to what you're saying, right?
yeah, so right, so exactly, right. So so we were trying to find an extension generated by a we were trying to find an extension such that the associated torsor here does not map to one. That's an equivalent way of saying it. Is that right, Omar?
Yeah, yeah.
Yeah. And then so and then we asked Michael Singer, who pointed us to this paper of Lourdes Juan and Arnie Ledet. So thank you, Michael, for pointing us to kind of this was really, I think, pretty much the only example that we could find ultimately, uh, which produces non-trivial D-torsors for SO3 which give Picard-Vessio extensions. Okay, so here's kind of how the example works. So let K be a differential field such that SO3 over that differential field has non-trivial algebraic torsors. Okay, then one can find, if that's the case, okay, so assuming that one can find two elements in K, A and B, and you set up these matrices Q and P, okay, and you let H be the coordinate the coordinate ring or the Hopf algebra associated to SO3, and you define and you let X be kind of a matrix generating this be kind of a generic matrix for H, and you define Y to be the product of X and P, and then you take T to be the ring generated by Y, and then they see that there's a map, there's an action, there's this coaction making the variety of T into a non-trivial right SO3 torsor. Okay. And then they show that if they're going to define, so if they're going to define so if they're going to define a derivation on T, which is equivalent by the fact, defining a derivation on the coordinate ring is the same as giving a D variety structure to V of T. So they show that if 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 you can find some matrix B such that this defines a derivation on T, then a necessary and sufficient condition, it's necessary and sufficient that B has to be exactly of this form for some elements. Actually, I didn't say what alpha, beta, and gamma are here. Okay, for some elements, alpha, beta, and gamma. Okay, and maybe I'm missing a condition here, but they show that if one takes the constants, maybe the complex numbers, and you join three differentially independent over C elements, and you set A equal to Y1, this should be gamma 1, B equal to gamma 2, alpha equal to gamma 2 again, beta equal to gamma 1, and gamma here equal to gamma 3, then this satisfies the above conditions, and this fraction and frac of T is going to be the desired Picard-Vessio extension. So that's how the example works. And so, right, so to me, like because GLN has trivial Galois cohomology, I was really confused initially because I felt like whatever example we found of this had to be outside of the linear case. But because even in this example, one can find an equation. The point is that if you're looking for the point is that you can't find a D variety structure on SO3 that gives this Picard-Vessio extension, but you can find a D variety structure on a torsor for SO3. But because GLN has trivial Galois cohomology, you can find a D variety structure on GLN for this example. So that was a little bit confusing to me. So because of that, we were trying to find examples outside of the linear case. So take some kind of elliptic curve and find an example where you have a strongly normal extension coming from generated by the solutions to a D variety structure on a torsor for an elliptic curve, on a non-trivial torsor for an elliptic curve. So I think Omar and I are both really, really interested in trying to find an example of this, and it's interesting to note that there doesn't seem to be an example in Colchin. So if anybody has leads on this, that would be awesome. And I think we're both really interested in working on that. Okay, thank you.
All right, thanks. Let us thank David for his nice talk. Do we have any questions for David? Feel free to unmute yourself and ask the questions.
Can I ask a question?
Yeah, of
Yes,
course.
please.
Yeah, so can we quickly go back to the sketch of the proof you suggested, David? Just for me to, yeah, that one. Right. So I guess when you say that X must have pi type bounded by delta, uh, you were deducing this from saying that G has pi type bounded by delta, right?
Yes,
But,
yeah,
but I mean, G is it's just some delta algebraic group, right? So
yeah.
there might be no pi equation satisfied by G, right?
I see. I
Right?
see.
It's like if
Right.
you take G to be algebraic, just take G to be algebraic,
Yeah,
right?
right. If G is
Then
if G is
algebraic
algebraic, then right.
has maximal differential dimension, right?
Mhm.
So I think that might be why. Yeah, I agree that for intuition is great, but I think for the argument, I'm not so sure that it goes right. Does that make sense?
Right. So yeah, so the right. Yeah, yeah. Yeah, right. I right because okay, right because what I was thinking of was if X is internal to something which has pi type bounded,
Oh yeah, for sure. Yeah, yeah. Then it's fine.
then then it's fine, right? So if it's a torsor, then it's pi
But,
type
but in
bounded.
this but in this case,
But
the
but
it's internal.
G
It's,
simply
it's
might
internal
not
to
be.
G, but G doesn't have the pi type boundary, right? So you don't expect X to be like a sharp point business. X shouldn't be a pi type a sharp point business, right?
Uh-huh.
Because
Uh-huh.
X could again, if X is algebraic, G is algebraic, X is algebraic, then they will have maximal delta dimension, right?
Yep.
But you just want to identify those two things. But it might be worth saying that what we actually used in the paper is this result of Anand, right? That differential algebraic groups and differential torsors, they always embed.
Embed into an algebraic torsor, into a purely algebraic torsor. That yeah, that's what we use. Yeah.
Yeah, exactly. My last comment is exactly coming out to your last slide. I mean, I would be very interested to see more examples, especially as you say in the nonlinear case, trying to find something that is just that there is no sharp or logarithmic equation in any group where the Galois group embeds. Like this sort of example will be interesting. Yeah.
Yeah, yeah, I agree, right? Because somehow here in this example of this paper with SO3, there's no equation on SO3, there's an equation on the torsor for SO3, but if you pass to GLN, then there is suddenly
Yeah,
then there
yeah,
is an
exactly,
equation.
exactly. So there's an equation in GLN and SO3 lives in GLN, but is there an example where you just cannot embed it into a group and find an equation in that group? So which is gonna come from nonlinear examples, right? So yeah, it's a good question, I think. Thank you. Thank you for the talk, David. It's very nice.
Thank you. Thanks. Yeah, so Omar and I we tried to look at examples. What the first thing you need is you need an elliptic curve with a torsor that has no K point. So you have an elliptic curve over field K, and you need a torsor which has no K point and has an invariant it has an invariant vector field, or it has a derivation on the coordinate ring, or it has a section of this twisted tangent bundle, and you need that it satisfies no new constants. You need that. So we were looking for an example of this, and uh we weren't able to build one. Okay.
Any other questions for David?
I,
Yeah,
well,
go ahead.
yeah, may I ask, excuse me. So sorry, my voice is losing. When you separate the derivations into a d and a delta, is there any way that if I just give you a set of derivation pi, that you can choose the d?
You can choose.
I mean, what is the property to single out one particular delta?
Um, so if I understand correctly,
I mean, is it true for you pick any delta to separate it and the theory would go through, or Is there some
So
property about this particular delta that let it go through, let the theory go through?
so 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 the way that the theorem the way that the theorem works is you first pick a set X, which satisfies a condition with respect to the partition. So um so one could choose a different one could choose I think arbitrarily the partition, and then for any X satisfying this condition with respect to the partition, the theorem would hold. So if
So,
I understand
so
correctly.
the question would be, for what delta that you choose that such X exists or is plentiful? Is that correct then?
My intuition is that they would be plentiful for any partition. But actually
So
Omar would
there's no
maybe have.
particular choice for the delta then.
Yeah, can I add something, William? Yeah, hi, William.
Yeah, also hi William. Nice to hear
Hi,
from you.
hi, Omar.
So if you take any X, right, there is a result of Colchin. It is in Colchin's book saying that there is a partition, and so there is this delta, such that X has this property, that the pi bounded property. So given an X, you can
Mhm.
always find this delta, such that X has pi type bounded by delta by a result of Colchin. Yeah.
Okay, thank you. So the delta depends on X. Is that correct then?
Yeah, I mean, if
I
you
mean,
start with an
in a
X,
given X,
given X, say X is a pi
given X
differential
without the
variety.
bounding situation, then you can find a partition so that
Yeah,
X actually is having the delta bounding
yeah,
condition. Is that correct?
that's right. That's right.
Thank you.
Great. Any other questions? All right. If not, let us thank David again.
Yeah, thank you.
Thank you everybody for coming.
All right. And I think maybe we meet next week. Let me double check. Yes, we do meet next week. So see you all then. All right.
Okay.
Bye, everyone.
Bye, thanks.
Bye.